Yeah, the stream just started.
Great. All right, so let me know when I should start sharing my screen. Get started.
It's 29 now. So if I understand correctly, a bunch of people will be joining the Zoom call as well.
Oh, great.
So maybe wait for them.
Sounds good.
Okay. Yeah. Okay, yes. Okay, so we have viewers.
Great.
Yeah, yes, we can go.
Okay. Should I start sharing my screen then?
Right.
Let me get that started. All right.
Right. Let's just start off. Okay, well, I'm here today with Daniel, assistant professor at the University of Georgia. And the topic for today is Ouroboros and connections between arithmetic and geometry.
All right, thank you so much.
Let's start with the title.
Yeah, sorry, Areeb, I'm having a little bit of trouble understanding your audio. I'm wondering if maybe you're getting a bit of feedback from your computer or something like that. But yeah, so maybe I'm not sure, but maybe your question was what is an Ouroboros? Is that right, or what does the title mean?
Right. Let's start off with the titles.
Yeah. So okay. So what I want to talk about is some connections between arithmetic and geometry, and I've decided to draw them with an Ouroboros. So what is that? That's like a snake that's eating its own tail. And so the goal of this discussion, at least for me, is to convey some of the ways that algebraic geometry and a few other fields, so I've written algebraic topology and low dimensional topology here, also kind of feed on each other, and how input in one area can be used to say interesting things in other areas. So I want to try to convey at least some of the flavor about how algebraic geometry, and I'll explain what that is in a little bit, which feels like a very geometric and maybe a subject which is not so obvious, how it could take input from number theory actually is like very heavily influenced by number theory, and then vice versa. So I want to explain how some algebra geometric ideas, so even some purely geometric ideas, can really influence number theory, and then depending on how much time we have, I might try to say a little bit about a couple other fields, so algebraic topology and low dimensional topology, but I think there I'll probably only be able to give an idea of what the flavor is, and not too many details. Do you have any questions about that, Areeb? Does that sound good?
Yeah, sounds great. Just right now, let's just, well, what's topology?
Yeah, so what's topology? Yeah, well, maybe I should start by saying what algebraic geometry is, right? And then I'll try to give some these other things. Yeah, so what's the situation? So what kind of objects are we interested in when we do algebraic geometry or number theory? And then I'll talk a little bit about how they're influenced by topology. So suppose you're given like a system of polynomial equations here. So here, each of these things I'll write that they're polynomials. So one way to write that is that they live inside of the set of all polynomials in n variables, which is denoted with C adjoin x1 through xn. So what are some examples of such things? So an example of a polynomial. So what are some of your favorite numbers, complex numbers, Areeb?
Well, there's one,
Okay,
Very
1 is
important.
1. So let's take
Zero
x1.
is-
Oh, 0 is another one. How about some I don't know. Let's take like pi maybe times x1
Pi.
x maybe e to the 2 pi I over 7 times x3 to the 8th. Okay, and so on and so forth. So this is an example of a polynomial. So you just take some numbers, some complex numbers. So we took 1, which Areeb gave me, and then, well, if you multiply 0 by something, that's not so interesting. So I ignored 0. And then I multiplied x1, x2 by pi, and x3 to the 5th, x3 to the 8th, sorry, by e to the 2 pi I over 7. So, okay, so what is a polynomial? It's you take a bunch of complex numbers, you multiply them by your variables to some powers, and then you add those things together, right? Yeah, so these are algebraic objects, which are what we're going to study. And we're going to study the situation where we have a bunch of them, and we want to look at the set of solutions to a system of polynomial equations. So as an example, and I'll give a lot of examples in a little bit, but maybe one such system, which you might have seen before, is if you just take y equals x squared. That's a system of one polynomial equation. It's the same as y minus x squared equals 0. And if you graph the real solutions, that looks like a parabola. Right. Great. But of course, if you put much more complicated polynomials here, you'll get much more complicated shapes, as we'll see in a little bit. Okay, so what is algebraic geometry about? It's about the geometry of the set of solutions. And usually you look at the set of complex solutions. So you look at the set of complex solutions. And then you might ask questions like what is the shape of that set? What shape do you get? So Areeb asked what topology is. So topology is, broadly speaking, the study of shapes. And so at least one way that algebraic geometry intersects with topology is if you have a shape defined by some polynomials, like this parabola, well, you can ask, like, from a topological point of view, what shape do you get? And of course, I mean, algebraic geometry is about a lot more, as we'll see, but at least that's like the sort of starting point. Like, what shapes can you get this way? And I'll give some examples in a little bit. Okay, so this is what I would call the sort of motivating like slogan of algebraic geometry. What shapes do you get from polynomials? You can ask a lot more complicated questions too, and we will later on. But let me before doing that, let me just say a word about what I mean by number theory. So by number theory, I mean, well, let's say we have some very special polynomials. So maybe we don't have pi or e to the 2 pi I over 7 here or something. What if we just have polynomials with like rational coefficients? So what if we had like, 1/2 x cubed plus x squared plus, I don't know, 7 x3 to the 5th equals 0, and then also like x1 x2 plus x3 to the 7th equals 0 or something like that. So this is a system of two polynomial equations with rational solutions. You could still graph the complex solutions to the system. It would be some shape, but I want to understand something about the arithmetic of the solution. So what about what questions you could ask are like, what are the solutions in the rational numbers in Q, or the integers Z, or maybe in some other arithmetically interesting fields. Like, if you're an expert, you might know about finite fields or p-adic fields or that kind of thing, and we'll talk about that later on. So in particular, so this is what number theory asks. So what about what is the structure of the set of the solutions? So for example, are there any solutions, or is there a finite or infinite set? Or if you have or the sort of really interesting questions that are very mysterious are, well, if you have a rational solution, that's also a complex solution, right? So it gives you, so maybe if you had maybe if your set of complex solutions looked something like this, so it maybe had some interesting shape, well, the rational solutions are some points on this shape, right? And you might ask, how are those points distributed? So that's some kind of, already we're seeing some kind of interaction between algebraic geometry and number theory in our questions, but we'll see later on that the behavior of these sorts of rational solutions is really heavily influenced by the geometry of the underlying situation. Okay. So
that sounds great.
Yeah, great. So let me give some examples maybe. So here's So here's the first example. It's a very simple one. So if you look at the equation x squared plus y squared equals 1, that's a circle, right? So these are the real solutions. So these are the real solutions. So where x and y are real numbers. You could also graph the complex solutions, and the complex solutions would look like, what they would look like is a sphere minus a couple points. So the complex solutions would look something like, a sphere minus a point. So this is some kind of picture of the complex solutions. Okay, but let's now try to understand the rational solutions. So Areeb, do you see any rational solutions to this polynomial equation? So where x and y are rational numbers?
Well, that's my favorite numbers, 1 and 0.
Right, yeah. Oh yeah, you even gave me those numbers earlier. Great. So okay, so here's the point 1, 0, which is the solution to this equation, and it's a rational solution. There's also 0, 1, and there's -1, 0, and so there's a few solutions. So how would we generate more? Well, there's an easy way to generate a lot of solutions. So what you can do is you can take a line through one of your rational solutions, which has rational slope. So let's take this line to have rational slope. And then it's a little exercise which you should try at home, that this other point of intersection is also a rational solution. So this is a technique called stereographic projection. Okay, and there are infinitely many lines of rational slope. There's one for each rational number. So that gives you infinitely many rational solutions. So so what we just discovered is infinitely many lines give infinitely many rational solutions. Okay, and now well, that tells us something. Already, again, we're seeing some kind of geometry interfering with our arithmetic. So understanding the structure of lines here, which is, okay, very simple geometry, lets us immediately see that from one solution, we can generate infinitely many solutions. All right, so let's try maybe a more complicated example. So let's suppose we have an equation of the following form. So y squared equals x cubed plus ax plus b. And here, let's just assume for simplicity that a and b are rational numbers. Okay, and depending on what a and b is, what they are, sorry, the shape of the graph might change. So here's a picture of maybe the real solutions. Again, depending on what a and b are, as you change a and b, this will kind of deform. And then the complex solutions to this are going to look like a donut minus a couple points. So they're the surface of a donut. So this is the complex solutions. So those are going to look like the surface of a donut minus a couple of points. And a curve defined by an equation of this form is called an elliptic curve. Okay, so again we can start trying to use geometry to understand the set of solutions. So in this case, depending on what a and b are, there might be no solutions. There might be just one solution. But if there are two solutions, we can start to think about what's happening. So if you have two solutions, you can draw a line through them. The line will again have rational slope because it's a slope between two solutions with rational coordinates. And this third point here will also be a rational solution. Okay, then you can do some other things. You can flip this point over the x-axis, for example, to get another rational solution. And now you can keep playing connect the dots, right? So now you could connect, for example, this point to this point. And now we get another point, and we can reflect that over, and so on and so forth. Then we can connect these 2 points, just for example, and then we get this point. Okay, and you can keep going and going. And anytime you draw a line through 2 of these points, well, it's usually going to hit at some third point. You can also take, if you're really fancy, you can take a tangent line. So you can take the tangent line at this point, for example, and that'll give you a point over here, and then you can reflect it and keep going. So even if you just have 1 point, you can already start generating more points, again using lines. Okay, and this procedure might keep going. It might keep going forever. Like you might be able to generate infinitely many points this way, or maybe the set of points you generate will start repeating, right? So in this case, you can get either finitely many. So there's two possibilities. So here you can get either finitely many solutions, or infinitely many.
Daniel, what you're writing right now, can you like keep it a bit far from the bottom?
Oh, sure, yeah. Okay, so let me, I can even move it. Yeah, so here we can have either finitely many solutions or infinitely many solutions. And sorry, I had to shrink that.
Thanks.
It's a little harder to read. Yeah, so those are the possibilities so here I've described what happens when you have a quadratic equation. So you get something which is a circle, and then as soon as you have 1 point, you get kind of infinitely many points, but you might have no points. So for example, if you look at the equation x squared plus y squared equals 3, this has no rational solutions, which is not so obvious. So if you would like a hint, so this has no solutions. And a hint is that to check that, you can reduce modulo 4. So suppose you had 2 solutions, maybe just for simplicity, assume they were integer solutions, and now divide the whole picture. So divide both solutions and the number 3 by 4, and look at the remainders. And then I claim that you'll be able to see that this has no rational solutions, or no integral solutions at least. And then here we saw that as soon as we have 1 solution, we get at least a few, but maybe this process terminates. It's so complicated, we can't really see that there are going to be infinitely many solutions or not. So what I want to explain now is how actually, so here I drew a sphere for you, and here I drew kind of a donut, and I want to explain how the geometry of those shapes is actually influencing what's happening. So this was kind of an amazing discovery of Faltings in the 80s, and it was conjectured by Mordell much earlier. So here's the Mordell conjecture or Faltings theorem. And what it tells you is that in the simple case where you have just kind of a surface defined by polynomial equations, so here we're looking at the geometry, the set of complex solutions to some polynomial equations, well, the arithmetic of those polynomials is going to be influenced by the underlying geometry. So we saw already that if you took a quadratic equation like x squared plus y squared equals 1, you can get kind of a sphere. If we took this cubic equation, like y squared equals x cubed plus ax plus b, you'd get kind of a donut, or the surface of a donut. And then if you took a higher degree equation, what you'd get is a donut with many holes. So here I've drawn one with 2 holes, but maybe you can imagine that there's a bunch of other holes in your donut in the middle. So what Faltings theorem says is it tells you what the arithmetic of the polynomial system of equations that defines this looks like. So in this case, we've already seen what can happen. In this case of a sphere, so this is called genus 0. Maybe let me write that over here. So in this case, you can have either infinitely many solutions, rational solutions to your system of polynomial equations, or you can have no solutions at all. Okay, and that's actually not so hard to see. We already explained why it's true. As soon as you have 1 solution, you can just use lines through it to generate infinitely many. All right. So now the situation in genus 1, so the case where there's kind of a 1-hole donut, like a normal donut that you might have seen, is much simpler. It's much more complicated. And this is probably, in some sense, the least well understood situation, although there's a lot to say about the higher genus case as well. So in this case, you can have either no solutions, so no rational solutions, or you can have finitely many solutions. Or you can have infinitely many solutions. So in other words, kind of anything goes. And why is this? Well, as soon as you have 1 point, you can start drawing lines. So for example, the tangent line, to start generating more points. So that's so either we have no solutions. If we have 1 point, we can start making more solutions, more points. But that procedure might terminate. You keep generating more and more points, but you might only be repeating the same points you started with. Or maybe you don't ever repeat, and then you get infinitely many solutions. Okay, and then the really amazing thing, and this is what Faltings proved, which is that if you have genus bigger than 1, so here, if you have genus bigger than 1, then there's only finitely many points. So there's either no points or finitely many points. So what I want to stress is that something really amazing happened here. So we had a system of polynomial equations.
Can you give us an example of a surface? Can you give us an example of a curve that would have genus greater than 1?
Oh yeah, sure. So for example, if you take y squared equals x to the 10th plus 1, this will have a bunch of, it'll give you a surface with a bunch of holes. I would have to think a little bit to figure out how many it is. I guess it would give you one with 4, a donut with 4 holes. Yeah.
Okay.
So if you just take y squared to be some high degree polynomial in x, that'll have lots and lots of holes. Okay, and then the claim is that this doesn't. Yeah. Sorry, were you asking a question, Areeb?
Also, we got a question from the live stream.
Yeah.
Are the punctures and complex solutions because we're not taking the solutions at infinity, like we're not projectivizing?
Yeah, that's exactly right. So I wanted to avoid discussing projective varieties. So yeah, the punctures are exactly because I'm writing down non-homogeneous polynomials here. So if you wanted to get things kind of without punctures, what you would do is you would homogenize this. So for example, you write down like y squared times z to the 8th equals x to the 10th plus z to the 10th. So that's a homogeneous polynomial of degree 10. And then you'd only view the solutions up to simultaneous scaling. So, right. So if you have a homogeneous polynomial and you have a solution to it, you can just scale all the coordinates to get a new solution. And we want to view those as the same. So this is a way of kind of compactifying these sorts of surfaces or varieties in general, but I'm avoiding that for now. Yeah. So this was an example here. Yeah. So the kind of amazing thing I want to convey is that, okay, we have the system of polynomial equations. A priori, it's pretty mysterious. But suppose the set of solutions is a surface. So the set of complex solutions is a surface. So that tells you something about the arithmetic of the solutions. So that what surface you get tells you, well, for example, if you, as long as you're not in one of these two cases, it immediately tells you that you can't have infinitely many solutions. So just from that, we already know that this polynomial, y squared equals x to the 10th plus 1, only has finitely many rational solutions, which is kind of an amazing fact. So maybe just let me give you one more, I think, appealing example. Let me add a slide here. So I think there's a famous, sorry about that. There's a famous example, which is if you take the equation x to the n plus y to the n equals z to the n, right? So and then you look at rational solutions. Rational solutions up to simultaneous scaling, just like we were discussing. All right, so what is, well, we want to know how many there are. So what was the question? So the question is, how many solutions are there? Rational solutions. And this question had a famous name. So it was Fermat's last theorem, right? So Fermat's last theorem was the conjecture that any solution had the form that required either x or y to be 0, right? So that's it's a very simple characterization. Well, so we could ask how that fits into our paradigm, right? So what shape does this equation define? And what it does is, so this equation defines a donut, if you'd like, with how many holes? Let's see, I guess it's with n minus 1 times n minus 2 over 2 holes. So if n is 3, you get 1 hole, and then we can't say very much. But if n is bigger than 3, so if n is bigger than 3, this theorem of Faltings we just mentioned implies that there are only finitely many solutions. So that doesn't quite give us Fermat's last theorem, which asks for a complete list of all the solutions, but it tells us at least there's finitely many. And maybe just a remark, so Fermat's last theorem was proven in the 90s. By Andrew Wiles with some help by Richard Taylor. And the ideas were quite different from this, but if we have a chance, I might say at the very end a teeny bit about the ideas. All right. Do you have any questions about that, or have there been any questions in the chat so far?
Not the chat. So I was just wondering, is there anything you could tell us about where the number n minus 1 times n minus 2 divided by 2 comes from? Because
I see.
n minus 1 choose 2, for example.
Yeah. So it is n minus 1 choose 2. So one way to think about it is if you take a product of n linear forms, so a product of n linear polynomials, so that'll have degree n. And what will the set of complex solutions look like? It'll look like a bunch of lines, right? And what you could try to do is you could try to count the number of holes in the picture I drew, and you'll see you get this many holes. So what you can imagine is that taking this picture. I'm sorry?
No.
So what you could do is you imagine you're taking this picture and then breaking it up into a bunch of lines. And in some sense, the number of holes will stay constant. And that's one way to see where this number comes from. Yeah, this is not, by the way, I mean, this is not a trivial fact. Like the fact that this equation gives you a surface with this number of holes is like you'd learn that in your first course in algebraic geometry, but it's not at all obvious. All right. So hopefully I've conveyed a little bit about the flavor of how you can go from geometry to arithmetic. So how the geometry of a shape defined by polynomial equations can tell you something about the arithmetic of the polynomials defining it. So I want to give you a little bit of the flavor of how to go the other way. So here's a theorem proven by Ax-Grothendieck. So Grothendieck was one of the 20th century mathematicians who more or less rebuilt algebraic geometry from the ground up. And I think this is a theorem that gives you some idea of the power of the techniques he used. So suppose you're given n polynomials in n variables. So I've written them as f1, x1 through xn, and fn of x1 through xn. So you can view these n polynomials as a map from Cn to Cn. So what do I mean by that? Well, if you have n complex numbers, you can plug them into these polynomials, and then you get n new complex numbers, right? So here's the Ax-Grothendieck theorem. So suppose this map you get from Cn to Cn is injective. So everything in Cn gets hit at most once. Then the theorem is that it's also surjective. Okay, and that's not at all obvious. There are plenty of just continuous maps, for example, from C to C, which are injective but not surjective. But this is something very special about polynomial maps. And the really incredible thing is that the proof is via number theory. So the proof goes via reduction mod p. So I want to give just some very slight idea of what the flavor is. So first of all, suppose we, instead of working over the complex numbers, suppose we were working over a finite field. So for example, you take the integers, you look at the remainders of all the integers when you divide by p, some prime p. So that gives you the numbers 0, 1, 2, 3, 4, 5 up to p minus 1. And those numbers you can add and subtract and multiply just by adding and then taking the remainder when you divide by p. So for example, p minus 1 plus 2 would be p plus 1, but when you divide by p, the remainder is just 1. So suppose we, instead of having complex polynomials, we had polynomials over a finite field. So suppose we had f1 through fn, which are polynomials with coefficients in this finite field, fp adjoint x1 through xn. And suppose that this map we get, so f1 through fn, which gives us a map from fp to the n to fp to the n, was injective. Well, then I claim it has to be surjective. Do you see why?
Well, they're finite sets.
Yeah, exactly right. So if you have a map from a finite set to itself, if it's injective, it has to be surjective. Okay, so this is some kind of baby case of the result. So we proved it over finite fields. So now step 2 is, well, let's go back to our original situation. So suppose we have f1 through fn, not with complex coefficients, but with integer coefficients. Well, then we can prove it just by reducing mod p. So reduce the whole situation mod p. So we know we get some polynomials which are surjective mod p. And moreover, this works for every p, right? For every prime number p, at least where your map remains injective. Okay, and now you have to do a little bit of algebraic geometry. So you have to argue that after reducing mod p, your map is still injective for lots of p. And then you have to argue that if you check surjectivity mod p for lots of p, then you've also checked it over the complex numbers. So that requires the use of something called the Nullstellensatz, which I don't want to explain, but it's a standard technique in algebraic geometry. Okay, and now let me, rather than write on the bottom of the page, let me add a new page and indicate, I think, the miraculous step here. So the miraculous step is, well, what happens? So what if your polynomials don't have integer coefficients? So what if f1, let's say, is, pi times x1 cubed plus the Euler-Mascheroni constant times x2 to the 7th plus, I don't know, some other Chaitin's constant times x1, x2, and then some other stuff. Well, this you can't reduce mod p, right? So what do? Well, the observation, and this is the observation that underlies like a lot of the beautiful interactions between algebraic geometry and number theory, is that these polynomials, well, you have finitely many polynomials, and each one of them only has finitely many coefficients. So you can work just over the ring, so work over the subset of the complex numbers just generated by the coefficients. And this is an arithmetically interesting ring. So this is a ring that you can reduce mod p and do all the sorts of other things that you would do in number theory. So this you can reduce mod p. So at least one of the key ideas of the proof is to take a number like pi and reduce it mod p, which I think is kind of amazing for some prime p. Okay, and I don't think I can give the details of the proof in this talk, but I want to stress that this is a statement just about polynomials of the complex numbers that you can prove via number theoretic techniques. All right, so I just want to finish up by giving a couple other, a bit of a flavor about what sorts of things are on the cutting edge. So this is stuff, that's mostly from the 60s through the 80s. So what are people thinking about now? So the first thing is I just want to tell you a little bit about a conjecture. So this is called the Bombieri-Lang conjecture. And what it is it's a massive generalization of the theorem of Faltings I mentioned from before, which told you that if you have a surface defined by polynomial equations, then the set of rational points is controlled by the geometry or topology of that surface. So the Bombieri-Lang conjecture is a conjecture about the same sort of situation, but not just for surfaces, for algebraic varieties, so for sets of solutions to polynomial equations of any dimension. And what that conjecture says is that if X has general type, so that's a generalization of being a donut with at least two holes, it's some notion of kind of negative curvature, which I'm not going to be precise about. Then if you look at the set of rational points, so the rational solutions to your system of polynomial equations, they're not dense in the complex set of solutions. And this word Zariski here means something even stronger. It means that So this means that not only are these rational points not dense, they satisfy, so the rational solutions satisfy an additional polynomial equation to the ones defining your original variety. Okay, I would say this is a conjecture that we know almost nothing about. It's so far on the cutting edge that we've made very little progress. But there's very recent work. So for example, by Brian Lawrence and Akshay Venkatesh, who just won the Fields Medal, which at least studies sorts of cases of this that we previously didn't have a lot of control over, or cases of this in related conjectures. So this is something that is a massive generalization of the work we discussed earlier, which is sort of ongoing. All right, I want to give you a couple more examples, and then maybe I'll see if, well, maybe Areeb, did you have any questions about this or anything else we've discussed so far?
No, not really.
Okay.
There've been no questions on the chat either.
That's all right. All right. So finally, I just want to finish by telling you about my favorite theorem, which is the Weil conjectures, which were proven by Dwork, Grothendieck, and Deligne. And what they say is that in a vast amount of generality, the topology of the set of complex solutions to a system of polynomial equations controls the number of rational points. So the set of rational solutions, not over the rational numbers, but over finite fields. So I can explicitly say what happens. So suppose X is a system of polynomial equations. Over a finite field, say Fp. Then what Weil, who made this conjecture, suggested is defining a zeta function, which counts the solutions to these polynomial equations. So this is kind of like the Riemann zeta function, if you've heard of the Riemann hypothesis. And here's the formula. So it's kind of a crazy formula, but it's worth it. So what you do is you take the sum from k equals 1 to infinity of the number of rational solutions. So here, let me use this to denote the set of solutions over the degree k extension of the finite field, Fp to the k, divided by k, and then times t to the k. All right, so yes, this is some funny formula. So the conjectures was that, first of all, this is actually a rational function. This was proven by Dwork. So this doesn't really reflect topology yet. So two, just like the Riemann zeta function, it satisfies a functional equation. This was proven by Grothendieck. But the really incredible thing is that Grothendieck's proof realized that this functional equation was a manifestation of Poincare duality, which is a sort of extra structure on, let's say, smooth compact manifolds. Well, orientable manifolds. And then finally, it satisfies an analog of the Riemann hypothesis. And that's a little too complicated to explain in this talk, but I can tell you at least one manifestation of it. So if you have a rational function, it looks like one polynomial divided by another polynomial. And what you can do is look at the degree of p minus the degree of q. So this is some integer. And this integer here is, in good situations, the Euler characteristic of x. So what do I mean by that? So suppose you, instead of having polynomial equations over Fp, you had polynomial equations over the integers. So the coefficients were integers, and you reduced them mod p. Then you could look at the set of complex solutions. So that would be some shape. So this is the set of complex solutions. You could break it up into points and lines and triangles and pyramids and higher dimensional simplices, so the analogs of pyramids. And you could take the number of vertices minus the number of edges plus the number of faces minus the number of sort of three-dimensional faces and so on. So it turns out this number, which is called the Euler characteristic, is independent of the way of breaking this up into triangles, and it's called the Euler characteristic. So the amazing thing is that this purely arithmetic generating function here detects this very topological invariant of the space. All right, maybe with that, I'll just show you my last slide. So I think I'm out of time, but I wanted to say something about modular curves just because this is a test. And here, these are some pictures of tilings, which are also closely related to interactions between number theory and geometry. But maybe we'll pause there and see if there are any questions.
All right, maybe just real quick, we should mention what manifold is.
I'm sorry, I'm having a bit of trouble hearing you, Areeb. Could you say that again?
Maybe we should mention what a manifold is.
Oh, sure. Yeah. So a manifold is it's a space, a shape that locally looks like the space you know and love, Rn. So it's a space where you can cover it by blobs, and those blobs are each open subsets of Rn. So just n tuples of real numbers. And then they're glued together in some smooth way. So for example, a sphere is an example of a manifold, or all these shapes I've drawn before. Intuitively, it's a shape which has some smooth structure. So a shape with no corners or edges or anything like that. Does that help?
Right. Sure.
Yeah, so this, if you haven't seen this Euler characteristic before, maybe it's familiar from Euler's formula, which tells you that if you have a polyhedron, the number of vertices minus the number of edges plus the number of faces is always 2. And then before, when I drew these sorts of pictures, so here, if you take one of these shapes, there's a generalization of Euler's formula that says that if you divide it into triangles, the number of vertices, so maybe let me just write it as V minus E plus F, won't be 2 anymore. It'll be 2 minus 2 times G, where G is the number of holes in your donut. And so that's the Euler characteristic is a massive generalization of that to any sort of nice shape with good finiteness properties. All right. So maybe let me turn back to this slide with the cool picture and see if you guys have any questions.
Well, the stream doesn't have any, and
do you have any, Areeb?
Well, yeah, let's get into it. Yeah, what are those?
Oh yeah, so okay, so these are modular curves, or these are pictures of really the modular curve. So what this is, loosely speaking, is if you look at these sorts of special equations from before, so elliptic curves. So this is the space of elliptic curves. So a point of this corresponds to one of those elliptic curves. And I just wanted to include it in the talk because your program is called tessellate, and here this is some kind of hyperbolic tessellation of the upper half plane, or a tessellation of here this is the hyperbolic disk, the Poincare disk. And I don't think there's much I can say that it will be accessible, but maybe I did want to give the flavor that at least a lot of the sort of beautiful interactions between analysis and number theory and geometry pass through modular curves. So these spaces of elliptic curves, and you know, so even tessellation itself is at least a little bit related to these connections between arithmetic and geometry.
Wow, you've really sold it to us on the last one.
I'm sorry?
You've really sold it to us on the last one.
Yeah. I'm glad you like it. Yeah, and I urge you all to look up the Weil conjectures and Faltings theorem and the Bombieri-Lighting conjecture. I mean, there's so much more to say about this stuff than I can say in 45 minutes. Yeah. Cool. All right. Well, if there aren't any more questions, I guess you know, I should thank you guys for having me on. It was a real pleasure. Yeah. Thank you as well. All right, great. Then I I guess I'm good. Let me stop sharing. Good luck with the rest of this program, and yeah, let me know if you let me know if any questions come up. I'm happy to answer questions via email or however else you'd like to get in touch. Cool. All right. So should I log off? Great. Bye-bye.
Great, I think that's it.